Thank you for joining us. This is Design Project Group 3. I'm Cameron Porter.
This is Ryan Martin.
And this is Jordan Humphrey. And today we'll be going over our analysis of a proposed wind turbine improvement. As our baseline for comparison, we chose the Block Island Wind Farm, located about 10 kilometers from Rhode Island, seen here as the red dots on the map. According to the National Renewable Energy Laboratory, this area sees an average wind speed of 9 meters per second.
At this wind farm, there are 5 GE Haliade 6 megawatt turbines at a hub height of 106 meters and a rotor diameter of 150 meters.
Our proposal is to increase this hub height to 140 meters because at greater elevations there is a higher average wind velocity and the wind is more consistent over time. Some challenges with this solution are the increased stress on the tower and foundation and the higher costs associated with building a larger tower. To demonstrate the benefit, here is the equation for power generation from the wind and how it relates to velocity, and how wind velocity increases with elevation for a given local reference height and velocity. The results can be seen in these graphs. An increase in wind velocity, however, also leads to an increase in thrust.
Increased thrust results in increased bending moments and torsional moments on the tower. 3 moments acting on the tower were considered. First was the moment at the base of the blades, denoted by M sub beta. The second was the pitch moment, denoted by M sub z. The third was the yaw moment, denoted by M sub y. The 3 moments are depicted here in the diagram. Both torsional stress and bending stress were considered for the analysis of the tower. The torsional stress denoted by tau was a result of the yawing moment of the tower. The bending stress, denoted by sigma sub b, was a result of the pitching moment of the tower. The principal stress and the maximum shear stress were both used to compare to the yield strength of A36 steel.
The foundation analysis was simplified to a monopile in the seabed. The API standards for this give soil resistance as a function of depth, angle of internal friction, effective soil weight, loading type, and pile diameter. Many of these can be found from API's tables with respect to sand. The results of these calculations are depicted in this graph of depth versus resistance, with several possible pile diameters. Ultimately, these are the end results of our analysis.
The power generation at 106 meters is 3.95 megawatts, while at 140 meters it's 4.29 megawatts, which is an 8.7% increase. Max principal stress is 12.22 MPa. A36 steel yield strength is 250 MPa. The tower dimensions are 3.5 meters for the outer diameter, while 2.5 meters for the inner. The monopile dimensions is 60 meters deep and 6 meters diameter.
These results and calculations are crucial to the design of our project. However, as with any large-scale engineering project, environmental factors must be considered. An environmental survey was conducted for the original project and covered items such as avoiding a right whale migration. Other topics worth considering are bird populations nearby, complying with FAA regulations, minimizing sound pollution, and maintaining a clean visual environment.
Finally, we looked at economic feasibility. The original wind farm cost $290 million total, about $58 million per turbine. By comparison, the current tallest turbine in the world at 178 meters costs $81 million per turbine. Our proposal, therefore, would be somewhere in between. As further validation, GE is already working on an even taller turbine called the Haliade X. Through this project, we were able to analyze the effect of increasing hub height on power output. Our analysis revealed that it would require strengthening the structure of the tower and the strength of the foundation to withstand increased forces. Upon analysis, the proposed tower structure and foundation would in fact be able to withstand a 140-meter hub height. Our proposed technology would result in increased and more consistent power generation. Thank you for your time. This project was performed by university students, not professional engineers, and neither the authors nor the University of Missouri-Kansas City guarantees its success or safety.